So welcome back, and we'll continue with the three-dimensional flows, and we'll finish off these notes from last time. So if we're looking at three-dimensional flows, of course, if we're looking in the world of boundary type layers, you might say in steady flows, here's an external potential flow, and that's dependent on two coordinates, right? Streamwise coordinate and radial coordinate in general. And within the boundary layer, there might be more, and it's unsteady, so there's three coordinates and unsteady. And that's a nice way to break down problems, especially when you're doing turbulence modeling. It's interesting in these external potential flows. I was talking to a friend at Penn State Aerospace the other day, and we were talking about solutions of Navier-Stokes equations outside the boundary layer. And often they can be reduced to like a nonlinear potential set of equations. And they actually have analytical solutions in a lot of cases for using the method of photographs. And I mentioned this before in the class. And there's very rare time to actually find someone who uses photographic techniques. And I might just ask the class, does anybody remember what a photograph is? It's an esoteric thing today, but it used to be really popular before general CFD came about.
Is it a plot of position and velocity?
Yeah, it's like a plot of position and velocity, sort of like what we did with the Lorentz problem, right? So instead of x coordinates, our dependent variables actually be the velocity components. And you actually kind of plotted a type of photograph with the Lorentz equation, right? If it's in like a velocity plot. Anyway, let's, I think we might have a shorter class today, which might delight you, especially on a beautiful day here in Florida. Let's just review our equations, right? Remember, we have conservation of mass and x momentum and z momentum. So, oh, this should be a y. No, w. It's okay. We can interchange y and w. That's okay. Did I misprint my equations? No, this is okay. I'm sorry. This is a total enthalpy. Yeah, I think I really would also prefer, I don't know why I did this, a y momentum equation. Oh, yeah, and I have my x momentum. So those are general equations. And also here, you can see that we can rewrite this in terms of, well, okay, static enthalpy. So here's the definition, right, total enthalpy of static enthalpy, and you see there's W, that's the cross stream coordinate. And you'll see that we've retained these pressure gradients. So in the boundary layer, x is the streamwise direction, and here z is the cross-stream direction. And if you remember in a previous class, we noted that in higher speed turbulent boundary layers, you can't always neglect this cross-stream pressure gradient product, which could be bad. And at the edge, so if we go out to the edge of the boundary layer, so here's our boundary layer, there's the wall, here's our velocity coordinate. Right here is the edge of the boundary layer. So this is why I mark these as like a little subscript E. And as we previously discussed, like in this equation summary, all these equations can be reduced here into like a turbulent boundary layer. It's like a boundary condition at the edge. And that's what the subscript E means, right? So if we're in a three-dimensional nonlinear potential flow at the edge, and it should be a nonlinear potential flow at the edge, right? Because that's where the turbulent boundary layers meeting our compressible nonlinear potential flow. It should be, because of the reduction to two coordinates, we can write u sub e of x, and we is a constant, something like that. there should be some sort of non-zero WE, right? Because there should be growth of the boundary layers as you progress downstream. Okay, now if we make a steady assumption from up here, once again, inside the flow, then we should have this compressibility, and okay, I've reverted to U again. We have our x momentum, and we have our total enthalpy. So I'm sorry about using different variables for the cross-stream direction. I set this on Sunday after working on a DARPA program for a while, so I apologize for that mix-up. And once again, every energy equation, right? Okay. More summary. We have our mean kinetic turbulent energy equation, right? So we have 3D equations, we have the boundary layer equations, we have our boundary layer edge condition, and to kind of close up the system, we still need other equations. One might be mean kinetic energy. So you can see here we're tracking the x velocity component and the y velocity component. If we add them up, that should have units of energy with kilograms per meter cubed. And we talked a lot about these terms when we expanded them out. So it's the same thing. And I should say that if you look at this term, we can simplify this a bit more for boundary layer flows. And this goes phi tilde times tau y bar minus rho v prime bar. So we notice dimensional analysis for turbulent boundary layers, this inequality is true. And with these approximations, this term here, which is u tilde tau xy v prime right here, we can simplify our whole set with the same dimensional analysis this way. And we'll take these approximations and put them in 1.77. And I noted here a few things, and not going to write them, I'll just read them to you. I said that equation 1.77 is a mean kinetic energy equation. It's unsteady, two-dimensional, compressible for turbulent boundary layers. And you can take this continuity equation way up here. Where'd you go? Right here, 2.170. And we can take 1.77 and simplify it here in 2.178. So what does this track? You can see this is tracking u bar squared. And we've dropped the v term, which is good because we decoupled it in the time domain term. So if you use a marching technique with like fourth order Runge-Kutta, it's greatly simplified things. So that's basically the Reynolds-Stress trace tensor. And more complicated models might look at Reynolds transport equations, and that's right here. So we can take these particular terms and rewrite 270, which is up here. There. Excuse me, 2.170. And simplify them a bit. These are pressure work terms, and I'll note that the first term on the right-hand side of 2.180 is called, in community, the turbulent viscous diffusion. And the second term is the turbulent energy dissipation. Okay, so then we can write a general form for our Reynolds stress. You can see right here, we got ui uj prime bar. That's time. So this is your transport. Everything on the right side are sources, sinks, and basically like convective type terms for that. And just a few notes about this equation. And remember, in turbulent boundary layers, we noted that are in 2 dimensions, that the mean velocity with the boundary layer has 2 components. That is boundary layer. And 2D has 2 components. And we can be k equals 1 to 2, for example. We would drop the 3rd component, right? So there's no 3. And the fluctuating velocity components have 3. G, k equals 1 to 3. So that should reduce the equation a little bit. So for 2-dimensional flows, this equation 2.81 would have, what, 6 total equations, which is a lot to do. So in a general 3-dimensional flow, we would have to handle them all. In boundary layer theory, we would be handling of course, 3 components, but it's going to result in only 6 equations. Okay, so what are the dependent variables in that set? They would be u prime squared, v prime squared, w prime squared, u prime v prime, c u prime w prime, and v prime w prime, which is a lot. So if it's a 2-dimensional flow, we might say that these last 2 terms are going to be 0 due to symmetry. And if we add the 3 equations for u prime, v prime, w prime, we would get the turbulent kinetic energy, right? So k is addition of u prime squared, v prime squared, and w prime squared. So those are good things. And you could also just do all this by just taking this equation, setting I equals j, basically. That's the trace. So you sum from 1 to 3, and we would obtain that turbulent kinetic energy. So if we let q equals u prime, so this is our turbulent kinetic energy term. Sometimes call it k. Later in a lot of the papers just call it k or TKE. A lot of the papers I've written, I wrote capital TKE. And some people call it q. So it just depends on the person, I guess, you deal with. And we'll also define a new variable called phi, and we'll call that the mean turbulent energy dissipation function. And this will be defined in 2.183. So for unsteady, compressible flows, which are the best flows, 2.81, equation 2.81, can be greatly simplified even more. And then we'll have 4 equations, which are for u prime v prime bar, u prime squared, v prime squared, of course, and w prime squared, as we need that span-wise velocity component. Okay, so if we look back at 2.182, right here, and we look at partial xi p ui prime, which is right here, we can make this dimensional argument that in the turbulent boundary layers that are in study, PV prime is going to be much greater than PU prime and PW prime. And I'm just kind of summarizing dimensional analysis that's been done in previous papers. They've also made these observations about gradients of velocities in the turbulent boundary layer. And here's another set of them. So instead of just sitting here and reading them, I've given you the notes. You can check that out yourself. And we've also rewritten ui prime ta I k double prime in terms of the turbulent kinetic energy. And the same thing for this term using dimensional analysis here, this term here, and partial this term here. Okay. Anyway, after you reduce all that, I'd like to just make a quick note, because this is pretty in-depth analysis. If we use all these relations and assume that partial ui prime partial xi, which is the D'Alembert condition for the fluctuating velocity, is small, and using equation 1.2, whoops, excuse me, equation, running out of room here, 2.130 and 1.31, we can write this final transport equation for TKE. So let's just look at this equation using all this dimensional analysis and a few different definitions. What does this equation mean for unsteady turbulent boundary layers? Well, it represents the local change in TKE. It represents turbulent energy convection. It's the second term here. And, well, it's actually this second term here. This is term number 2. This is term number 1. And now on the right-hand side, going from left to right in this direction, the 4 terms are the turbulent viscous diffusion, the turbulent kinetic diffusion, the turbulent pressure diffusion, that's this term here, and finally the turbulent energy dissipation. So when you're trying to close compressible turbulence models, we're going to look mostly in compressible models in the class because that's what they're generally formulated for traditionally, and a lot of the famous models are that way. People actually reference the different terms in these equations and might even do a whole study and paper just to try and find good closure models for these particular relations and try and relate them to known variables in the base Rand's equations like U bar and V bar. Okay, I think people are still copying that, so I'll leave that there. So back up here in the TKE equation in the unsteady boundary layer, the energy is much larger than the averaged energy as fluctuations. We multiply the continuity equation by this term, negative 1/2 q squared, and add the particular expression from this operation, and add it to 2817, we'll get this intermediate equation, 2.188. So some notes. Okay. Sorry about that. Okay. Now, if this particular term, which is the stress tensor, just say, for instance, that we neglect that, and we apply the Prandtl's boundary layer, should write Prandtl's approximation to 1.81, then we can get something a little bit closer to 1.82 for the trace, and we recover a TKE equation working on fluctuations. And then this is just a general derivative of the material derivative, which we substitute in 1.90, and we get 1.92. So what does this equation mean? Well, we can write an equation for each of the turbulent energies. Which are V prime squared bar and W prime squared bar, by setting I equals J equals 2 and I equals J equals 3 in 2.81, which I'll just go up here to remind you, 2.81 way up here. which is our Reynolds-Stress equation. Okay. Way down here again. And that's the Reynolds-Stress. Okay. And then we can write a single equation for the shear stress by letting I equals 1 and J equals 2. So we have now single equations for shear stress. And that might also be useful for doing something at the wall. So these prime variables should be going to 0 at the wall or become very small because we're in the viscous sublayer. So here's the first component. So this is number 2, right? And this one's number 3. This is nothing but the off-diagonal stress term. I'm sorry, so this is the, I should explain that better. Here's our stress tensor. So here's our V term, here's our W term, and this is your UW term. Right here. Yep. Here's U, sorry. Okay. Okay. So for compressible flows, incompressible flows, this whole thing for TKE can be reduced here. And so in the class, sometimes I'll refer back to these different particular equations for boundary layer modeling. Now, those are all the equations for differential form, and before the differential forms were really used, they're more popular today in like CFD. A lot of people did integral forms, and in fact there's something called like Prandtl integral forms of the equations, and actually it's just a little over the 100th anniversary of Prandtl and people using these forms to make predictions, without computers. So there's actually some special journal articles coming out that have calls for articles to kind of like write historical papers on the boundary layer forms, which are kind of interesting. But I want to note some of these integral type equations quickly, based on these equations, just so you are aware of them. And, well, of course, all these equations are basically unsolvable right now, or very difficult to solve. And as you can probably gather, that there's so many different forms. And I think one of the hardest things to do in the CFD world is to choose which equation is appropriate for which problem, because there's lots of formulations. But what if we integrate the equations across the boundary layer? Then they're no longer partial differential equations in some case, but they become ODEs. So I'll write they might become ordinary differential equations. And ODEs, I think, are a little bit easier to solve than PDEs, just from my experience. And probably a lot of you have the same experience too. That's why the first computer project was solving a set of ODEs, not a PDE. But the good thing is, it's just a mathematical operation. We are integrating away some things, but they're still exact in the boundary layer, which is very good. So these are called the integral boundary layer equations. That's why they have their name, because we are integrating them across the boundary layer. And just for examples, because it can get even more complicated in 3D compressible flows, we're going to just look at steady 2D flows, which is pretty useful for boundary layer theory. Okay, so here's a particular equation, and you see I've written this x momentum equation in terms of having UE in it. Okay. So if I non-dimensionalize this equation, and I integrate it in the y direction, So this integral here, you see it's dy. Here is the boundary layer, there's the wall, and this is the y direction, and there's a boundary layer. You can see something interesting here. So what did I non-dimensionalize by? Rho e over ue, of course, and pulling it out. So you can see ue here, this is here, and rho e ue, this is also here. So if I look at some of these terms like rho u over rho e, what should that go to at, say, the boundary layer edge, or even at 20 boundary layers? That should be rho e over ue. So even way out here, this is ue out here, or rho e ue, right? Because it's just a nice plate flow or something like that. So these terms should be going away. 1 minus u over ue, this should be going to 0 at high values. If I wanted a particular property of the boundary layer, instead of writing infinity here, I could have set it to, say, some value of y, for instance, right? And then I would have this integration done from the wall to, say, some point y. But I'm letting it go to infinity, which is fine, because, of course, all these terms and these equations you can see are going to be going to 0 as the integration goes to infinity. So a few little notes. You'll note that partial u, partial y, and u prime v prime bar go to 0 as y goes to infinity, right? So there's no derivative of the streamwise velocity component outside the boundary layer in this flat plate case. And certainly the turbulent quantities like Reynolds stresses would be going to 0 outside the boundary layer because there's no turbulence. It's just a nonlinear compressible potential flow. And also there should be something at the wall. Well, of course, u equals 0 at wall. That's just a given no slip condition. But since we're dealing with turbulence, you probably don't always note that u prime v prime, for example, goes to 0 as y goes to 0. Okay, so if we take 1.298, we can write it now as the boundary layer thickness and theta, like a momentum thickness. And so this equation here, 1.98, can be reduced to something that's like an expression for the shear stress of the wall if we integrate across the boundary layer. We can then non-dimensionalize that, and a new little parameter comes up called h. And h is nothing but a non-dimensional number, which is something like, I have to remember it, delta star over theta. And this is called the shape factor. So when you calculate a turbulent boundary layer with a contemporary code, you can calculate all these quantities. And they're important for aerodynamic analysis. If we have an isentropic ideal gas, this is an equation that can be written. It's often introduced in gas dynamics. ME here is, of course, UE over CE, right? That's the velocity at the edge of the boundary layer divided by the local speed of sound. And once we do that, we're almost through this set. We can then write a differential equation for theta, and CF appears right here. And CF is the skin friction. So those of you who've worked in some aerodynamics work, skin friction, of course, is a non-dimensional way to look at, the stress on the body locally. So it's often something you would want to try and predict, like an airframer company like Boeing, Airbus, or Lockheed. What's the skin friction in your vehicles? You want to minimize that. If there's no flux through the wall, VW is 0, then we can reduce this equation even further, and I can write the skin friction, it appears here. And then we have a nice differential equation for that. If it's incompressible, it reduces even further. And I can get rid of ME, and that makes sense because ME is usually a non-dimensional parameter that's useful for compressible flows. So these equations, what's the bottom line? 2.202 to 2.204 are called the momentum integral equations. And you can see they're nice differential equations that only involve streamwise position and the shape factor. So through integration and non-dimensionalization and a little bit of simplification, noting that turbulence goes to the wall of 0, you now have basically like a one-dimensional equation that only involves boundary layer thickness and shape factor, and you can estimate skin friction on an aircraft. So that was a huge advance, and it's ODE, meaning that for some simple configurations, I can actually estimate skin friction and therefore drag on like early vehicles. So these momentum integral equations were just used heavily from the time that Prandtl and his research group in Germany laid them down through the 1950s. And of course, in the 1960s, people started writing CFD codes in federal governments around the world to kind of replace this stuff. And another big bonus is they're applicable to laminar and turbulent flow, which is a nice bonus in life. Usually it's not that way. We haven't talked about the mean integral equation. I just want to note that quick, just to be complete in the introduction of these equations. So if I go back and I look at 2.133, and I'm going to be, I don't even know if it's in this set of notes. It might be in the last one. So you'll have to bring that up and multiply by UE squared minus U squared. So that's completely our choice. And multiply 2.135 by negative 2U. So that's our choice 2. We just multiplying both these equations through. And we're going to add those two equations, and we're going to simplify. We're going to get this equation 2.205 right here. And let's just look at it for a second together, see what we see. We'll see it's 1/2 of partial x, and we have terms like rho e ue cubed, that's a boundary layer edge. Rho u over rho e ue, so it's right non-dimensionalized. And if we imagine integrating this equation, if we wanted, what happens, you can see like from 0 to infinity, these terms here, like this one, and this one in particular, and probably this one by implication. If all these other terms go to 0, the right-hand side would have to go to 0. That should also go to 0, right? So we can imply that for large integrations from the wall to large y values, mu partial u partial y should go as negative rho u prime v prime, but outside the boundary layer anyway, that would be 0 also from a previous observation, right? So this is about 0 outside the boundary layer. Okay. So we can also rewrite this right-hand side as equation 2.206, where we've defined the shear stress this way. And we'll substitute 2.206, this rewrite of negative u partial tau partial y, back into 2.205 up in here on the right-hand side term. And then we'll integrate in the y direction just like we did with the previous set of differential equations. And we will get this equation. And we'll introduce a new definition. This is the energy thickness. So a way I think of that physically is just like we have a boundary layer thickness. That's just, as we explain to people, that's about where the velocity is from the distance to the wall, about 99% of the ambient velocity. Is just a general way of saying it. Well, this is like saying this is the distance from the wall to where we're at about 99% of the free stream total energy or enthalpy. Okay? So that's how this might be explained here. You see it's also, after integration and simplification, it's also an equation that's only involving a differential equation d dx, and there is a term d dy here in this integral. But this should go to a constant number anyway, because we have 1 minus rho over rho e and u over ue. And we're going to set that to just a term d, and we rewrite that here. It can be simplified. And what does that mean? Well, here's an observation. This is what we call the dissipation integral. It's probably called the dissipation integral because it has something to do with energy, right? U prime V prime, which is a Reynolds-Stress term. And what does it mean? It denotes the viscous work done in the boundary layer by the shear stress mu partial u partial y and negative rho u prime v prime bar. And we can dimensionalize that and write it as equation 2.10. And I'll read that again because my writing's so bad, I apologize. It's called the dissipation integral, and it denotes the viscous work done in the boundary layer by the shearing stress mu partial u partial y and negative rho u prime v prime. And you can write that dimensionally right here. And this is, in this case, this is not drag coefficient, this is the dissipation integral coefficient. So this also can come up in compressible high-speed flows when you calculate certain things. Only a few more notes, and we'll be completely done with all the equation formulation, and that might make you happy. That's okay. And let's just make a note about the turbulent energy integral equation. Oh, let me get my highlighter. All right. So if we take 2.187 and this is supposed to be integrate, sorry about that, from 0 to infinity, for a steady flow we'll get 2.12, or excuse me, 2.212. And with all the same boundary conditions, diffusion term should drop out at the boundary because there's no diffusion through the boundary. And this can be written in this way. And here, IQ squared is this term here. And this P and D, the difference, this is the difference between the production and dissipation of the turbulent kinetic energy through the whole boundary layer at any cross-stream location. I just said that from memory. I didn't have a note, which impresses me sometimes. And these are defined here as 0 to infinity of negative rho u prime v prime bar of partial u partial y dy. And d is from 0 to infinity of rho phi dy. So production dissipation of turbulent kinetic energy, generally right-hand side terms, and that would be governed through an integral of this IQ squared. If you're in equilibrium, I would hope that production of turbulence and the dissipation in turbulence, if we add them, they would be 0. And that would be an equilibrium boundary layer flow. But if you have shearing and some kind of work being done, then your production would be positive. Okay, with that, I'm going to sort of end just the overview of all the, I guess, formal introductions of all the governing equations and different ways they might be used. And then the question is like, okay, we have all these terms, and we need to kind of like create closure models. And that's kind of what we're going to start doing 2 classes from now. Because before that, we probably have to talk a little bit more about some of like the physics of turbulent boundary layers in terms of like length scales and things like that. But before that, we're going to talk about the second class project.